Yeah, here they are. Just let them get in. Come on. There we go. Well, before we continue with and hopefully finish today LHospitals rule, we're going to give you a kind of big picture thing. Everyone should have got a report. If you haven't got your report, you need to contact me and send in the email, the new email link that you want me to send it to, and I'll change it on my spreadsheet. We have got, what was I counted? 8 days, including today, left. We are well on schedule, so there's no problems that way. Anything else I need to tell you? No, that is it. Okay, so last time, and continuing with it, we're going to look at a thing called the LHospitals rule. And clever guy, Belgian, he figured out how to find limits of fractions. And what you do is you just take the derivative and of the top and of the bottom totally separately. Now, I'll emphasize again, that is not a quotient rule. Agreed? I'm not differentiating that fraction. I'm just differentiating the top on its own and totally independent of at the bottom. But he found out that this limit might be impossible to do. And the reason why it's impossible is that when you plug in A could be infinity or 0 as well. You get what's called indeterminate form, 0 over 0 or infinity over infinity. And this must be true before you do that, right? And I did show you an example where you didn't need to do LHospital. And if you did do it, you got an answer, but it wasn't the right one. So it's dangerous. Every time you do LHospital, check in case it works. If you get an answer, stop. If you get 0 over 0, your indeterminate form, then it's okay to do it a second. And in fact, I think there are a couple of questions where you have to do it a third time. So I'm going to start off with a pretty straightforward one just to get the show on the road. So let's do the limit as x equals 0 of 5x take away 5 cosines of x and 3x take away 3 cosines of x. And if you evaluate this, the top is 0, the bottom is 0, we're good to go. You put in an equal sign with a little L above it. That's normally the convention, so people know what the heck you've just done. What you're saying is, I am using LHospital. So it's going to be the limit as x tends to 0. If you differentiate this guy, you get 5. If you differentiate a cosine, you get a negative sign. So 2 negatives give you a plus. You get a 5 sine x. And on the bottom, you've got a 3, and you have a 3 sine x. And every time you do LHospital, you then plug in this case, x equals 0, and see what you get. Well, 5 times the sine is 0, sine of 0 is 0, so it's still 0. There you go. I mean, when it works, isn't it nice and tidy? It's just clean. Boom, boom, done. If you didn't have LHospital, I mean, wouldn't that be pretty impossible to figure out what the answer was? I mean, you plug in 0, you just get 0 over 0, and you're going, oh, it could be anything, right? That's why it's called indeterminate form, right? It's not, we're not sure what it's equal to. Now we are. We know its limit is 5/3. So today we're going to focus on less obvious ones. To me, obvious ones are, you don't need to do anything, right? You just apply the rule and you are good to go. Less obvious ones are ones where there's some kind of problem, you know, in the calculation perhaps, so, or in the algebra. So here we have a question like number 8, and it's a limit as u tends to infinity of e to the power of u over 5, and on the bottom we have u cubed. Now, if you put infinity in here, and e to the infinity is infinite, infinity cubed is infinite. We are definitely in determinant form. Now if you, oops, almost forgot to put it in. If you differentiate the bottom, you get 3u squared. And if you differentiate the top, you get that. But that's not all you get. If you want to think of that as 1/5 u, that's fine. But isn't this a baby chain rule? It's not e to the u, it's e to a 5th u. So this little guy up here is our inside function. And if you differentiate this guy, you get 1/5. Are you happy about where that 1/5 came from? Why it's there, right? Now, if you plug in infinity, you're getting nowhere because you're still in determinant form. So I'll do it a second time. And you differentiate the bottom, you'll get 6u. If you differentiate the top, you'll get that guy, of course, and you'll get times another 1/5. So it's now 1/25 I've got, right? A 5th that I had times another 5th that I've just got. And if you plug in infinity, you're still in trouble. So one of the reasons I picked this one was because you have to use LHospital 3 times. So you differentiate the bottom, you get 6. And you differentiate the top, you get times another 1/5, which gives you that. And now we can plug in infinity. And you get this guy, infinity over 5, or 1/5 infinity, over 6. Right. This is essentially calculations with infinity. And I've just said u there. And that u, here we go, it's infinity. Would you agree that infinity divided by 5 is infinity? And infinity to the power of infinity is infinity. And 1/25 of infinity is infinity. And if you take that infinity and divide it by 6, you still have infinity. Would you agree that if you multiply or divide or take infinity to a power, don't you just still get infinite? Still infinity. So that's the answer. Infinity is okay. It can be a limit. No way that one, so I won't do that one. Do a trig one. So we have the limit as x tends to 0 of 2x. Take away the sine of 2x. And on the bottom, I have 2x. Take away tan of 2x. If you plug in 0 here, you get 0 on the top, 0 on the bottom. Indeterminate form, we can use LHospital. If you differentiate 2x, you get 2. If you differentiate a sine, you get a cosine. So if you differentiate a sine of 2x, you'll get a cosine of 2x. Times the derivative of the inside function, so you get an extra 2. And on the bottom, that guy's 2. What do you get if you differentiate a tangent? What's the derivative of a tangent?
Secant squared.
And so the derivative of the tangent of 2x is the secant squared of 2x and a times 2, right? Because of the inside function. Are you comfortable where these extra 2's are coming from? Now, if you plug in 0, you get 2 take away 2 and 2 take away 2, so that's no good to us. So we'll do LHospital rule again. If you differentiate this guy, you get 0. If you differentiate a cosine, you get a negative sign. So that gets you plus the sine of 2x times another 2. So that's now 4. And this guy gets you 0. And a secant squared. Well, I'll forget about the negative 2 until later. Let's just do the derivative of secant squared x. Well, the best way to look at something like that is to think of it as that. So that makes me say, it's a chain rule. So when I differentiate it, it's 2 lots of secant x to the power of 1, followed by the derivative of secant x. Now that's one of the rarer ones, but it does have a derivative. And it is in the list of the 6 that we gave you when we did trig derivatives. I guess the question is, who's got a good memory? What's the derivative of secant x?
Secant x times tan x.
You nailed it. So I'm going to put that together and call it that guy. Now, we don't quite have secant squared. Do you see how we have negative 2 secant squared, right? Well, won't that just make this times negative 2, right? So I just didn't bother with the negative 2 because it was, cluttering up. Was that 2x or x? Oh, darn it. There's a 2x here, right? When you differentiate secant of 2x, when you differentiate the secant of 2x, you get secant 2x, tan 2x, right? Secant tan. And you also get what? Isn't this a Russian doll? So what else do you get? Times, well, the derivative of 2x, right? Times 2. That's what I was on. So, caught that just in time. 2 and 2 gets you 4. Those two combine to get you secant squared 2x. Then you have a tangent to 2x. So that's what we've got. Now I'm going to multiply it by negative 2. So we will have negative 8 secant squared 2x tangent to 2x. Now, all I'm doing here is really quite minor. And I'm also doing it a lot slower than perhaps I should do it in a typical question. Right, that's all I've done. I've essentially just removed the x's. Now, because I'm not doing LHospital, you see, I just use a normal equals. Now, if you put 0 in here and 0 in here, you are going to find that that's 0 and this is 0. And at this point, you should probably say to yourself, I don't want to do LHospital anymore. Because differentiating this guy, won't it just get uglier and uglier and uglier? There is no obvious end of the road if you do that. So at this point in here, I'm going to continue with the algebra and just see if we can rewrite this and simplify it in some way. So again, nothing here to do with LHospital. I can't think of anything useful right now to do with the top, so I'm just writing that down. Can someone tell me a different way to write secant squared?
1 over cosine squared.
Right, so how about 1 over cosine squared? Can anybody think of a different way to write tan x?
Sine over cosine.
And again, I'm probably taking a lot more lines than you would choose to do, and that's fine. Oh, while I'm at it, I can do a little cancel. It's just a minor thing. Can't I do that guy? Now we have, right now, that guy on the top. I've got a -2 left over on the bottom. And I've got a sine x, or a sine 2x, I should say, all over cos cubed 2x. I'll put a little bracket around that for emphasis. When you have a fraction, and it's on the bottom of a fraction, can't you basically just flip it upside down? So what does that mean? It means that I can rewrite this fraction like this. The guy that's on the bottom can now go on the top. So far, so good. So I've turned everything into sines and cosines. I've tried my darndest to get rid of fractions inside fractions. All I've left with now is, oh, those two things cancel. And so we are now going to be looking at the limit as x tends to 0 of cosine cubed 2x over -2. And if you put 0 in here, you get cos cubed of nothing over -2. The cosine of nothing is 1, so that's 1 cubed over -2. You have got the answer, -1/2. So we actually did solve it. But from here downwards was all algebra, trig algebra. Nothing to do with LHospitals. Any questions about that one? We good? So where should we go next? Oh, we'll do another trick. The limit as x tends to 0. I don't know. I think I do so many of these that every one of them starts becoming deja vu. Like, I think I've done this before. I don't think I've done this one before, have we? Does it look familiar?
We did that one yesterday.
This one? Okay, so I won't do that again. Let's do a log one. So
You did
we're
number
doing
11 yesterday too.
oh, thank you. God, well, that's good news. We do need a new piece of paper. We have not done this one. I can tell just looking at it, because this one is ugly, and the one after it is weird. So you've got an ugly and a weird to finish off with. Let's do ugly. The limit as x tends to infinity of x times the sine of 9 pi over x. And I hope it's kind of obvious that that's not a fraction. I mean, that's two things multiplied. It is not a fraction. So what's it doing here in LHospital? Well, since LHospital is so powerful and so good at getting limits, if you give me a question that's not a fraction, sometimes I can rewrite it as a really ugly fraction. And then I can use LHospital on it. So I am going to change this guy into this really ugly fraction. Algebraically, that's a pretty stupid thing to do, right? To take something that looks quite nice and make it look like that. But isn't this algebraically the same thing as that, right? A 1 over x is that guy. Agreed? Now, if you plug in infinity here, you get the sign of 0. And if you plug in infinity here, you get 0. So basically 0 over 0 is indeterminate form. So now I can do LHospital on it. And this is not pretty. If you differentiate 1 over x, can you trust me on this? But you could call it x to the negative 1 and then differentiate it. The bottom line is you end up with negative 1 over x squared. Can you trust me that the derivative of that ends up being that? Just to save some time. Now, if you want to differentiate the sign of this ugly guy, you're going to say, yep, this is definitely one of those chain rules. So you're going to get the cosine of this really messy fella. And then if you differentiate 9 pi over x, I could, and I will, put the answer there, but I'm going to do this one on the side. That's the guy I need to differentiate, right? Because you've differentiated, now I need to do the inside function. Well, I'm going to call this 9 pi x to the power of negative 1. Now I can do the differentiation. Multiply by the power and reduce the power by 1. And then make it look, style points, make it look like the original. Are you comfortable now that the derivative of that ends up being this guy? So when I differentiate the sine of 9 pi over x, I get the cosine of 9 pi over x times negative 9 pi over x squared. And I'm now, oops, I'm now just going to do some algebra. Okay. So I have the cosine of 9 pi over x. Negative 1 over x squared cancels out most of negative 9 pi over x squared. What gets left over? If you cancel this with this, what's left over?
9 pi.
Agreed? And if you don't like this, this is the long version of the same thing. I have 9 pi over x squared on the top. I have negative 1 over x squared on the bottom. I can take the top one and multiply it by the reciprocal of the other, because that's essentially a division. I can cancel out them. The two negatives make a plus, and now I'm left with 9 pi over 1. I'm left with 9 pi. Does that help? If you want to do it the long way. Well, I don't need to do LHospital. I can plug in infinity. Well, I have the cosine of 9 pi over infinity times 9 pi. Well, that's the cosine of 0 times 9 pi. That's 1. So 1 times 9 pi. There's your answer. The limit of this fella is 9 pi. Looking good? Then we have one, well, that was the ugly one. This is going to, this next one here is going to be, where is it? I lost it. It was here a minute ago. I was looking at it. A version of 15. Actually, I don't think that's the one I wanted, but it's a good one to do anyway. This is a weird one as well. If I plug in infinity here, I get infinity times 1 over 0 essentially. And infinity times 0 is indeterminate form as well. What we need to figure out is how to make this a fraction. Right? We need a fraction to do L'Hopital. Algebraically, how could I rewrite that guy as a fraction?
Could you put the E on the bottom?
You could indeed. That's exactly what you need to do. Now I'll do L'Hopital. It's going to be the limit as x tends to infinity. That guy is just 9 x to the 8, the power rule. This guy is a chain rule. It's e to the x squared times 2x. And you should always be on the lookout for simplification. This x cancels one of them. So now I have 9x to the 7 over 2e to the x squared. Are you comfortable about this x cancelling one of those powers? Would you also agree this question is going to be long? You can just see what's going to happen. Aren't I going to have to do L'Hopital quite a few times? But that's fine. That's going to get me 63x to the 6, and 2x times that guy gets me 4x e to the x squared, which I can cancel a little bit and get 63x to the 5 over, I'm beginning to regret this question, but I've started it, I might as well keep going now. You can cancel an x, and then I can do L'Hopital again. And that gets me 315x to the 4, 8x e to the x squared, because basically I have an extra 2x. Then you cancel them down. And now I have 315x cubed over 8e to the x squared. You know that it's finishing. Do you agree? You know it's going to stop eventually, right? And I guess you just have the perseverance to keep going. So let's keep going then. I am definitely regretting this one. 945 x squared over 16x e to the x squared, which becomes 945 x's over 16 e to the x squared. Right. One more time. The limit as x tends to infinity of 945 over 32x e to the x squared. Now, when one side or the other ends up being a number, isn't that a good signal to stop doing L'Hopital? So I'm stopping L'Hopital. If you plug in infinity, then I get 945, 32 times infinity e to the power of infinity, which essentially is 945 over infinity, which means the answer is 0. So all that hard work to find out the answer was just 0. I think I should recategorize this one as really, really ugly. But it did have an answer. And one last one then. Let's do question 14, and that's us kind of, I think, covered all the obvious situations that you can get. And this one was the one that I was thinking about earlier and couldn't find, but now I found it. That guy, if you plug in 0, you'll have to trust me here, but you get 0 over 0, right? Well, you get 0 over 0. Sine of 0, 0. So cosecant of 0. Cosecant of 0, oh, you get 0 times infinity. Okay, that's indeterminate form as well, right? That's 0, that's infinite. Indeterminate. Okay, we need some fraction here, don't we? You can't do LHospital without a fraction. Any suggestions about one of these two guys being changed and ending up on the bottom?
Cosecant becomes the sign in the denominator.
And a cosecant then becomes essentially that, right? Actually, this one's going to finish pretty quickly. If I now do LHospital on it, if you differentiate the sine of 5x, you get the cosine of 5x times 5. And if you do the derivative of sine 10x, you get the cosine of 10x times the derivative 10x, which is 10. You can now plug in 0. 5 times the cosine of 0, 10 times the cosine of 0. The answer is a half. Now, isn't that the way LHospital should work? Not this 12 rows, keep going till you get fed up kind of one, but, clean, boom, answer. That's the way you would like it at least to work. Any questions on LHospital, or are we good? Are we good? Okay. I think that went well. That's just the feedback I'm getting by looking at you, which is why I like to see you. I think that went well. So we are on to our last section for this week. It's a little bit different than normal. You're going to have to wait with me for a second. I can't remember the number, but it's fine. I'll sort that out once I get the thing loaded up. I need to get Desmos up and running, because that's actually how we're going to do this. And I'm almost there. And it's section 4.5. We're going to look at curve sketching. I'm not quite sure what you are seeing right now. Okay, you're seeing this, aren't you? My hand in the paper. 4.5 is going to be very easy to do because technology has kind of advanced to the stage where things that you used to do, like when I was young, a long time ago, you had to do almost everything by hand. You've got to remember there was a time when there weren't graphing calculators, right? Or software that would draw graphing calculators even, right? So how did we in those days approach the problem of, I'd like to draw a sketch of a function? Well, this is the only version of this question I'm going to do this way. And that is, I'm going to do it from scratch. So once we've shown you this technique of doing it from scratch, we're then going to let Desmos essentially do everything for us. And what we could do if we wanted to is we could check that what Desmos says matches what calculus says. So let's put in some of the things that you would want to know if you wanted to sketch this cubic. Wouldn't you like to know, for instance, the x-intercepts and the y-intercept? There's only one y-intercept. There could be more than one place where it crosses the x-axis. Now, if you want to get the y-intercept, don't you just find the value of the function at 0, which in this case is 0. So that becomes 0, 0. You don't do it in paper like this, but I'm in a hurry, and you're just going to have to do as I say, not as I do. So there we go. Would you agree that's the y-intercept? It crosses at the origin. Now the x-intercept, if you want to get that, don't you solve when is this equal to 0, right? And I should have brought that down here for room. I'm going to pull out 3x as a common factor, and that leaves me with x squared, take away 6x plus 9 equals 0. And then I factor it a little bit more, and I get x minus 3 times x minus 3, which is basically the same thing. And I get x equals 0. And both of those tell me that x equals 3. So I have an x-intercept at the origin, which I already knew, and an x-intercept at 3. So right now, the only thing I know about this cubic is that it crosses the x and y axis at the origin, and it crosses the x-axis at 3. Isn't that what you would have done in 141? So I'm not doing anything here that's to do with calculus yet. Agreed? 141, sketching polynomials. Next thing I'm going to find are the local max and minimums. Now, normally you would find the value of the local max and min. That just means the y coordinate, but I'm actually going to find both the x and the y coordinate, because if I want to sketch it, I kind of need to know where the thing is and if it's a max or a min, of course. So to do that, I find the derivative, which is 9x squared, take away 36x plus 27, right? So if you differentiate that, 9x cubed minus 36 plus 27, and the derivative being 0 is going to tell me where the max and mins are, because when a derivative is 0 are the critical numbers, and critical numbers are where things like this happen. I would pull out 9 as a common factor here, and I get that. I would then factor my quadratic, and if I had time I would ask you, but we are kind of on a kind of time schedule here. I have something happening at x equals 3 and something happening at x equals 1, right? That's my two critical numbers, right? When the x coordinate is 3, the derivative is going to be 0. And when the x coordinate is 1, the derivative is going to be 0. So I will do my number line, and I guess I'll put in 0, 1, 2, 3, 4, 5. And I will do what's called a table of signs. I'll write down here I'll write down the factored version of the derivative. That's actually easier to work with. And I will find some test points. But first I have to put in that at that value there, the derivative is 0. And at that value there, the derivative is 0. And I'll put in my little invisible dotted lines just to emphasize that there are 3 separate regions that I need to find the derivative for. So I'm going to do a test point at x equals 0. That's one. 1 at x equals 2, and I know x equals 4. And for each of these, I'm going to find the derivative at that point. And if you find the derivative at 0, the answer is positive. If you find the derivative at 2, the answer is negative. And if you find the derivative at 4, the answer is positive. Can you check that later? But I'm pretty sure I'm right. So that makes this positive, this guy negative, this guy positive. Are we comfortable with the quick version of that table? Because we have done a few of them. Now that table will tell you all sorts of cool stuff, like it's increasing, decreasing, increasing, but want to also tell us local max and local mins, which is why I'm using it. So if you go to, for instance, at x equals 1, it's positive, means the curve's going up the way, 0, and then negative. There's a local max. So I know there's a local maximum at x equals 1. And the coordinates of that point then, which we don't typically bother about, but we will now, is going to be 1, 3, take away 18, I27, it's going to be 1, 12. And what about at 3 then? Well, it's negative, so that means it's, decreasing, then it's 0, and then it's positive, and that's a local min. And that's happening at x equals 3. And I want to know what the coordinates of that are. So it's 3, something. And that I'm definitely not going to do on my own. I'm going to go 3 times 3 cubed. Take away 18 times 3 squared. Plus 27 times 3. No. And do you know what? I should have realized it. Isn't it the x-intercept? 3, 0. Oh, that's cool. So back to my very badly drawn sketch. This fella. I know that x equals 1, y is 12. So I'm going to have to do a scale. 2, 4, 6, 8, 10, 12. At that point there, there's a local max. So I do a little thing that looks like this. At 3, 0, there is a local min, which looks something like this. Where was the y-intercept again? At the origin, wasn't it? So I'm going to have to come up quite steeply then. And then come down here. And then keep going that way. Okay, they made a bit of a mess on that side. But do you get the gist of the cubic shape? You could have done a pretty primitive sketch, but it doesn't have all the features that I would be interested in knowing. And that's when Desmos comes in. So here goes. I'm going to put that same guy into Desmos. I'm going to tweak some of the windows so it looks a little bit more like my scale. But apart from that, I'm not going to change anything. So based on my sketch here, I think I only need x values from about -1 to say 5. And I just realized I've got a 1 that I didn't get rid of. Right. And it looks like the y values go as high as 12. So I'm going to assume that there's a bit of symmetry going on. So I'm going to make this from -12 to 12. And now I'll put in the function. And the guy that we were sketching was y equals 3x cubed. Take away 18x plus 27x. And I think it's x squared. And why am I in capitals? And why did no one tell me I'm in capitals? Y equals 3x cubed. take away 18x squared plus 27. Right, when I hit this x, I want this guy to go through the origin. I want him to go up the way. I want him to come down and bounce off the x-axis at 3 and go back upwards. And the moment of truth, go for it. Didn't it do exactly what our sketch said it should have done? Isn't that? I'll stretch it out a little bit. That way, there. Cool. Now, we don't need to do any of that because hasn't Desmos kind of removed the need to do sketches by hand, right? The technology has advanced beyond our math, but I wanted to show you how you would have done it when I was a kid, right? That's how we sketch functions using calculus. Which again, it's maybe my picture wasn't neat, but wasn't it the same picture, right? So I knew I was getting the right answer. How are you going to do those questions? You are going to do Desmos, aren't you? And you're going to get a question. I think I've got time to show you. You're going to get a question like this. Oops, here we go. Here is the guy. Which one is the right picture? And I believe it was that one, wasn't it, for us? Actually, can you see what I'm talking about? Because I'm not
Is
sure
it the
what you.
same? Is it the same question? Because ours went up all the way to 12.
Oh yeah, they're going to change the numbers. Mine's went and changed to 45. Do you see that? Yeah. Okay. When you plug that into Desmos, won't you get one of these 4 pictures? So it actually, in this case, it ends up being that one, right? Because it's told me the answer. We cool? Which means that homework is going to take you about 5 minutes. Right? Because aren't you just going to plug it into Desmos? Now you're going to have to adjust the windows, right? Because, you know, sometimes Windows, it's a tiny little thing and you have to stretch it and then, you know. So what I mean by that is look at the scale, right? If I was doing this question here, wouldn't I do an X from -66 and a Y from -28 to 20 so that my Desmos picture would be similar scale to the ones that are in front of me? Because sometimes if you distort it, it's hard to tell. Yeah, mine's look skinnier than yours. Am I got the right picture? You know, that kind of thing.